55.
Okay.
Just get the screen ready so we can start sharp at 5:55 with the CoboTalks, and then we can move on to IHFC. And then, so
Is my screen visible?
just check. Uh, yeah, it is.
Perfect. I'll
So
be
just
starting in
keep
a
it to
minute.
this pause, and just you can start in. Actually, you can start in next 1 minute. Let's see how many people have managed to join. Mm, I guess they will start by 6 o'clock. Yeah, you can actually start. Maybe in 1 or 2 minutes, you can wait 1 minute more, and then you can start. Yeah, I guess you can start now. Pratik.
Welcome to CoboTalks, a monthly seminar series. Second Wednesday every month since 14th October 2020. 20 plus speakers presented on Cobotics. Our collaborating partners IHFC, BIRD, Cognitive Science Program, a Department of Humanities and Social Sciences. IHF Foundation for Cobotics, Technology Innovation Hub of IIT Delhi, a national mission on interdisciplinary cyber physical systems by DST, Department of Science and Technology, Government of India in March 2020. A Section 8 company, IHF Foundation for Cobotics, IHFC, was incorporated on June 13, 2020. About IHFC. Advances in sensing, computation, and autonomy are enabling robots and autonomous systems to enter real-world domains such as manufacturing, defense, medical, agriculture, etc., where machines must work alongside and interact with humans. We are entering an era of manned and unmanned teaming where humans and robotic systems must work together towards common goals. The four verticals of IHFC: medical, agriculture, industry, and defense. Our goals: human robot collaboration for enhancing human capability and reducing risk and improving productivity. Our objectives: research on novel technology areas of robotics and automation science, development of products for benefit of society, inculcation of startups, and promoting entrepreneurship in India. Our CQ: concept, collaborate, commercialize. From research to product. Grand projects of IHFC: medical simulator, human robot interaction control, rehabilitation robotics, drone applications, healthcare robotics, human robot interaction intelligence, intelligent sensing and secure communication, and Industry 4.0. Bird, a center of excellence at IIT Delhi. About Bird, biologically inspired robots and drones. The Center of Excellence on Bird, biologically inspired robots and drones at IIT Delhi is an evolution from its humble research activities, which began a few decades ago by its faculty drawn from the Department of Mechanical, Electrical, and Computer Science Engineering. Bird has 10 plus projects, industrial and academic, 27 plus members, including faculty, students, and technical staff across various departments of IIT Delhi. 150 plus publication in international and national conference and journals. 9 years of experience. Cognitive Science Program, a department of humanities and social sciences at IIT Delhi. Cognitive Science Group at IIT Delhi is to create a knowledge pool that can address relevant problems under the ambit of human cognition both for India and the world at large. It helps students acquire a strong background in theoretical frameworks and empirical approaches of one or more areas of cognitive science. Cognitive science is an emerging new field of study that endeavors to study the mind from multiple perspectives and disciplines by combining ideas, principles, and methods from psychology, linguistics, philosophy, computer science, and neuroscience. This knowledge is applied for developing a better understanding of how our minds, brains work while creating better products, tools, services, and policies. CoboTalks, leading the way in the human robot collaboration space.
Thank you, Ritik. Thank you, everyone, for joining in. Today, I would like to very warmly welcome you to this wonderful 37th edition of Kobo Talks, which we very proudly host as IHFC, where, as you have come to know, that most of you must have come to know that we are into collaboration and we look at many collaborating with many professors and many projects in terms of grant projects, startups, in our ecosystem, international collaborations. So IHFC is actually, I have Foundation for Robotics, and I would like our team to now present a small video on what IHFC does and what IHFC is for everyone to understand what IHFC is all about. So Ritik, if you could please play the IHFC video.
Robotics means collaborative robotics, where human beings and robot work together.
We work on technologies of the future. We look at ways in which these technologies will actually get deployed.
We are trying to build an ecosystem here. When we talk about ecosystem, it starts from the kind of research capabilities that we are able to build. How is that we are able to instill the sense of commercialization in all those activities? When we talk about research, it's not only papers or publications.
So we have chosen four major thrust areas, you may call it. One is called the medical robotics. The second is the defense robotics. Third is the agriculture robotics. And fourth is the industry 4.0 or industry 5.0.
The mission of IHFC and the mission of IIT Delhi, there's a lot of synergy. And so we are treating IHFC as an extension of the things that we anyway want to do. The first goal of success would be creating an impact in society through some value add in terms of technologies and ideas.
I would definitely want IHFC to make an impact, an impact wherein we see indigenous products being developed, wherein we see our ecosystem coming together to see that we as an entity, we as a country, we as an ecosystem are able to build products on our own. So we should have export-oriented products being developed with whatever research capabilities we have, and that is what we want to do as a part of IHFC.
Thank you very much, Ritik. Thank you. Thank you, Ritik. I think that has given a lot of people a very fair idea as to what IHFC does and how we are looking at empowering young minds and creating new entrepreneurs and creating a startup ecosystem. And along with that, we are looking at training young minds into creating something better for the country. We are working towards the Atmanirbhar Bharat, and all our collaborations are working to create indigenous built, created, ideated, conceptualized, and executed products in India. And with that, we have a lot of collaborations, and we've been working closely with many, many professors all over the country. And today on Valentine's Day, we decided, a very, of course, in our senses, love is a very important sensory feel that we all go through. But why don't we have a very apt talk, which is on artificial intelligence, augmented robotic neurohabilitation, which I had the privilege of actually visiting Professor Shyamanta M. Hazarika's laboratory in Guwahati when I visited it. And what I saw was extremely fascinating how he works with the mind and the senses, bringing them together to create something magical. To introduce everyone to Professor Hazarika, he's from the Biometric, Robotic, and Artificial Intelligence Lab, Mechanical Engineering and Mehta Family School of Data Science, and AI Institute, All India Institute of Technology in Guwahati. Uh, he aptly has been applying what you call artificial intelligence and robotics in healthcare, and sees that AI as a practice is accelerating change in robotic neurorehabilitation. So basically merging and marrying the world of robotics and neurosciences. And this is being primarily done to develop a novel way of technologies that would have profound impact in the lives of individuals who have neuromotor disabilities. So in this talk, Professor Hazarika will give us a good idea as to how the contribution of AI has been, driving this momentous transformation. And also he'll talk about the emerging technologies which are going to be, taking over the world and of course assisting human and everybody in the future to have a better life. So, of course, Professor Hazarika is a INAI sub DST Abdul Kalam Technology Innovation National Fellow. He is a professor of mechanical engineering and professor in the Mehta Family School of Data Sciences and AI at IIT Guwahati. Over here, he leads the Biometric Robotic and Artificial Intelligence Lab. Before that, of course, he has been a professor at Tezpur University and always been associated with cognitive sciences and neuroinformatics. Let it be India, let it be international with University of Bremen or University of Leeds. Professor Hazarika has been working extensively research on bionic prosthetics, robotic neuro rehabilitation. So I think it is very apt that today he's going to talk about all this, along with artificial intelligence and machine learning, how it's applied in our lives today to make our lives much better as we go ahead. So with that introduction and to give you an idea as to what we can expect in today's talk, I would like to hand over the mic to Professor Hazarika to take it over. Professor Hazarika, all yours.
Thank you very much uh, for such a warm introduction. I'm really privileged to talk to you about artificial intelligence augmented robotic neurorehabilitation. Let me share the slides and we'll begin. Hope the slides are visible to you. Are the slides visible? Can somebody confirm?
Yes, sir.
Yes,
Okay,
sir, it is
great.
visible.
Great. So let's begin for our artificial intelligence augmented robotic neurorehabilitation. It's indeed a privilege to be talking about it because of the very fact that robotic neurorehabilitation holds the key to separating the hype around AI from the hope that it holds for the future. And as engineers working on this field, it's very important for each of us to realize that we should not be carried away by the hype created around these technologies, but focus on the hope these technologies hold for bringing in a social change, to bring in society 5.0. So research within my group is centered around bionic prosthetics and intelligent assistive devices, particularly aimed at functional rehabilitation of the upper limb. But before I begin, let us focus on robotics in healthcare in general in the last decade. So starting at this 8 o'clock position and proceeding clockwise, we can see that laparoscopic robots are the success story of medical robotics, with applications including very interesting radical prostatectomy for and very interesting applications for bladder cancer, rectal cancer. Then came these continuum robots, which are robotic versions of the manual medical instruments, catheters, bronchoscopes, and colonoscopes. Then there was huge development in the area of non-laparoscopic robots, developed for varying applications, including electrode implantation in the brain, microsurgery inside the eye, and then suddenly came soft robots, which are used to create soft sleeves to assist heart contraction. And this is when we looked at also other soft tissues, including the hand, for rehabilitation of daily living activities. Assistive wearable robots is an area that has come and changed the quality of life of people. It is used to augment or replace arm and leg motion in case of motion impairment or amputation. And the focus of my lab over the last 3 decades have been working on intelligent bionic prosthetic hands and hand exoskeleton for rehabilitation. As you may have observed, we work in the area called robotic neurorehabilitation with our focus on these two verticals. So robotic neurorehabilitation actually seeks to incorporate advances in robotics with artificial intelligence combined with insights into neuroscience to define new methods for treating problems related with neuromotor coordination, evolving novel strategies for motor therapy, and also implements or devices which we call intelligent assistive devices for improving the quality of life. With that aim, we are working and we are looking at neuromotor recovery. So one thing that needs to be told at the very beginning is the fact that neuromotor recovery through physical and mental practice, the one that the physiotherapist tries, is based on the premise of neuroplasticity. That is, the capacity of the neurons and the neural networks in the brain to change their connections and behavior in response to some form of sensory stimulation, damage, or dysfunction. Now, robotic interventions come into play here because they can be used to harness the power of neuroplasticity for therapeutic purposes. And AI and machine learning comes to really implement what physicians call assistance as needed. That is, for retention of residual skills, you would have to assist with the minimum amount, nothing short, nothing more. And that's called assistance as needed, which does retention of residual skills and therefore promotes or accelerates neuroplasticity. And that is why AI and robotics coming together for rehabilitation is something that we are looking forward to. So we have a very simple translation pipeline for most of our work. We design and develop looking at the biology. So that's why we call it biomimesis or biomimicry. Thereafter, we look for the mechanical characterization of the device or the intelligent assistive support system that we are developing. We study the workspace or the forces, torques, whatever. That's a mechanical characterization. Once the mechanical characterization is satisfactory, we look for the functional characterization. That is activities of daily living through users with neuromotor impairment is what we try. And this cycle then repeats because we then need to come back to the design table to readjust and redesign a lot of things that we have taken a wrong step in the first place. After a couple of cycles here, we move on to really implement the machine learning or the AI-driven rehabilitation protocol, which is something that we are now actively working on in terms of evaluating the recovery and providing assistance as needed, as I was explaining you a little while ago. So that's the translation pipeline for most of the stuff that we do in the lab. This here on your screens is a prosthetic hand that we have been working for the last 15 to 20 years. And another that we have been focusing on recently in the last 4 or 5 years is the idea of the hand exoskeleton. Okay? So these are the two things which I will be talking of today to you. Show you how machine learning, AI, and robotics is coming together to make these things possible. Let's start with biomimetics or biomimesis of the human hand. So one would realize that the human hand is one of the most complex things. And if you want to really copy that human hand into an underactuated bionic hand, it requires designing it based on some functional objective criteria. So we have used something called the potential grasp robustness, the robustness of every grasp that it executes as the grasp quality metric, on the basis of which optimization of the hand design parameters like the optimum pulley radiuses, the spring stiffness, and the spring preload angles is undertaken. We also look at optimal actuators. So we define what this kinematic system has to do. So in our case, we think of allowing it to do 6 grasp types using about 70% of daily living activities. And then we work out the optimal number of actuators and couple joints. And for this, we solve a optimization problem. We have solved it using a non-traditional method based on some non-traditional methods like we have used is some form of So that's what that comes to us. And we then go on to look at and exploit the knowledge of the experience that has been gained over the years in terms of the anthropomorphic design to ensure grasp, human-like grasp, and we exploit frugal, innovative design ideas so that we land up in an affordable functional prosthesis or prosthetic hand. Now, when we are doing this, we are interested in actually exploiting the biosignals and making it an integral part of the human body. So electromyogram signals, particularly signals from the flexor and extensor muscles, is used to identify the grasp types for control of the prosthetic hand. And these muscle commands, they arrive at the muscles from the motor cortex via the spinal cord. And thereafter, we have roughly 300 milliseconds on which to acquire, process them, and classify them. So for a very early rudimentary model, somewhere around 5 years ago, we had used time domain features and principal component analysis, followed by a traditional radial basis function support vector machine for classification, and giving us some 98% accuracy in the grasp types being emulated. But then we realized that in order to have a really real-time product and copy the human hand, we need to do far more than that. And feature selection is an important part of any such architecture. So we worked on this and we have come up with our own feature selection method called the KPLS MRMR. Now, for people who are aware of what is MRMR, let me put it very clearly. We are talking of maximum relevance and minimum redundancy sets here. But KPLS refers to kernel partial least square. So it's a regression method that models a nonlinear relationship between a set of output data and a set of input data. MRMR refers to maximum relevance, minimum redundancy, and has been recognized as one of the best feature selection methods. So what we have done is we have worked out a KPLS based MRMR method aiming for easy computation, improving classification accuracy for very high dimensional data such as movement decoding or phantom limb perception that is being exploited for controlling of such prosthetic devices. And we have been able to achieve very high accuracy rates with very fast computation, real time. So let me take a minute to explain to you for your people interested in the academics here of what is the KPLS method. So most of us are aware that regression is an approach for modeling the relationship between a scalar dependent variable and one or more explanatory variables. In KPLS, what is done, or in PLS, the partial least square regression, it's a regression method that takes into account the latent structure in Y and the latent structure in X. These X and Y are decomposed into their latent structures in an iterative way, and the direction of the most variation of Y is obtained. The direction of the most variation of X is obtained. Next, the direction of the most variation of Y, that is the latent structure corresponding to the most variation of Y, is explained in terms of the latent structure of X. So thereafter, we map the original input variables to some high dimensional function space and then apply the PLS algorithm onto the transform data So this transformed dimensional space that I'm talking of can be be very high and even infinite dimension. And there the PLS is going to be computationally expensive. We solve this using the kernel trick, that is compute the inner product between the images of the pairs of data in the feature space. And that leads to our KPLS as method. So once we have the KPLS, then what we do is we look for the KPLS regression coefficients to determine the relevance of a feature vis-a-vis a feature score or a target class or another feature, leading to the relevance score and the redundant score. So we have a feature to class telling us how relevant it is, and a feature to feature telling us how redundant it is. So with that, we add the MRMR to give us the KPLS MRMR algorithm. So this is something that has changed the way we look at EMG, EEG classification. And we do very good feature selection and classification to get very interesting ideas. Okay, so we can do grasp very fast in terms of the bionic hand that we have created. Once that is done, we took ourselves, we pushed our boundaries ourselves. We said, fine, we can now do grasps. Our hands can pick up things, but can it do the bionic reflex? That is, if you're holding a glass and it is slowly slipping out of your hand, you hold it tighter. Okay? Or if you are holding a pen and it slips out, you're holding it tighter. But the tightness that you provide in both these grasps are different depending on what is being done. So we wanted to recreate this. This is called the bionic reflex. And we wanted to recreate this is bionic reflex, which comes from the spinal loop and not from the brain. So here we used and exploited something called reinforcement learning. So we created a reinforcement learning agent and run huge number of experiments in training to do a lot of slipping under a lot of domain randomization in terms of friction, in terms of stiffness. And the hand was exploring a number of ways it could grasp, and it was rewarded if it could do better. If it was not doing it properly, it was penalized. And the idea of the agent was to maximize its rewards. So it learned how to do the grasping and it could grasp. So the learn agent could, after a lot of training phases, that's called co-simulation. The simulator and the controller simulation is running together. And then the agent learned it. So for this, we had used something called deep reinforcement learning, in a deep learning based reinforcement learning agent. Okay, so that's something that gives us even the idea of the bionic reflex being recreated in our hands. So we have now a prosthetic hand that does the EMG because of the EMG being collected from the person wearing that hand, and it does all of the reflexes is very fast locally because of a reinforcement learning agent residing in it. So here is the bionic hand emulating grasp based on EMG classification and a lot of other experiments. So this is one functional rehabilitation that we have looked at. Now the expertise that we have earned in EMG control of prosthetic hand, and we wanted to utilize it in providing assistance in flexion of index fingers for people who have lost their ability to move because of stroke or other disabling diseases. So we started with trying to move the index finger for a stroke affected person and via the EMG being collected. And thereafter, our focus was then not on grasp, not on the hand any longer, but on the human grasp. So initially, the idea was biomimesis of the human hand. Our focus now is biomimesis of the human grasp. So we wanted to create a 5-finger hand exoskeleton. We looked for the kinematic synthesis is to ensure that all fingers and thumb follow the natural trajectory. And we then created underactuated mechanisms for the finger. And finally, we performed what is called pose analysis to analyze the behavior of the proposed device. And we obtained optimal link satisfying natural range of motions. And once we were able to do this, we then used a biodegradable thermoplastic uh, polylactic acid to really create our hand exoskeleton prototypes. Okay. And we have used linear actuators to control each finger. So now, interestingly, we have been doing a very interesting functional characterization of this. Once the mechanical characterization was completed early, we have now looked at if our hand exoskeleton with phalanges and articulations as being part of the kinematic chain, and if it could really follow the natural trajectory. So two conditions that it must satisfy. If it has to follow the natural trajectory of the hand, any point on this mechanism vis-a-vis any other point inside the mechanism, they must be circular in motion. And almost all of our fingers follow that. We have seen that for most of our fingers following such circles. And other is the DIP joint, when it rotates about the PIP, that also is circular. So these ensures that the fingertip follows natural trajectory. So this is when we were satisfied with the functional characterization of our device. We wanted to now put it to real use. And remember, my aim always has been to follow assistance as needed, nothing more, nothing less. So we fall back on data-driven systems. So recently, there are a lot of results which have demonstrated that it is possible to understand high-level concepts by learning. However, such algorithms are very data intensive, and the lack of data severely limits their performance. Therefore, we are now moving on and working on a new data set from where we want to learn relationships among objects and grasps in daily living activities. So we collect annotation of object poses, grasps, and relationships for target-driven grasp tasks over a set of objects from the YCB set. And we have custom-built data globe for this, where we have used finger TPS for the finger forces and FlexiForce sensors for characterizing the posture parameters. This has led to, and the experimental setup for this is that we are not only interested in the final grasp, we are interested in the reach to grasp scenario. So you approach, you grasp, you lift, you hold. All of these, we wanted to find out what is involved. So the force sensor and the flex sensors capture for us the posture as well as the forces involved, and we then look at them. We have been able to identify what are called grasp synergies. So if you look at the row at the top, you could see that for every force or for different objects, I could see how the 5 fingers, the forces are connected. Or at the bottom row, you could see how the angles are connected. So I could get a synergy understanding from this data. That synergy understanding, the grasp synergies understanding, could allow me to recreate the grasp in my functional device, the 5-fingered hand exoskeleton. So I could then perform range of hand movements and tasks with precision, agility, and coordination. And the functional characterization based on grasping of objects based on the synergies that is there as has been possible. And this is a data-driven approach, mind you. So we had collected data, we had understood the synergy, and then we have learned the concepts of grasping this rather than program each of them for one individual grasp. So we have learned it over the grasp synergies. Okay, so that's when I complete biomimesis of the human grasp. So if you recall, I started with biomimesis of the human hand. Thereafter, I moved on to biomimesis of the human grasp. And now the idea was that where is our progress vis-a-vis robotic neurorehabilitation? So one needs to understand that robotic neurorehabilitation and the agenda is that you should be able to really put the person back to performing his daily living activities, whether you use implements, which we call intelligent assistive devices, or you affect neuroplasticity by working on his motor area. So we look at what is called electroencephalogram or EEG. From the surface of the skull is collected, and we understand motor intentions in addition to electromyogram that I have been discussing so far, the signals from the muscles. So now we have two signals, one that comes from the brain. So we create what are called motor imagery EEG brain computer interfaces. Interfaces is based on the electromyogram signal. And we already have muscle signals coming. So now if you are an electrical engineer, you would love to have a control diagram. So our control diagram conceptually is this. We have the brain. The brain drives our muscles. The muscles are not strong enough to communicate to the musculoskeletal system. So we have given it to the robots to really actuate this system. But we add a twist to this story. We say we also get signals from the brain and we talk to the robot controller. So now the brain is not only passing signals for control, it is also being used as a sensor to understand what is the physical state or what is the mental state of the system that's going on. So we create such things and we call it the EEG EMG adaptive control, where we take EEG, the electroencephalogram signal, try to understand what it is trying to say. We take the muscle signals, the electromyogram, and for interaction between any type of intelligent assistive device and a human, we convert the feedback control loop where we take signals from the brain as well as signals from the muscle, and we get this coupling between them called the corticomuscular coupling, interaction between EEG and EMG. And here also we use our own feature selection, the KPLS, MRMR. Okay, so KPLS is something that we have been able to really exploit to a limit. And we worked out novel approach for estimating this. Now, I would take a minute to explain you this block because this is something that excites us. So as the brain tells us what to do and the muscles tell me what I can do, there is a mediator that we have implemented. And the mediator then decides whether the control should be automatic or the control should be passed to the patient. If the patient is doing good enough, the control is with the patient. Otherwise, the mediator takes it over and automatic control takes over. So this implements what we call assist as needed in the system. But then we realize that any form of motor imagery, prolonged motor imagery, if I want to do and I allow my patients to do, it causes mental fatigue. So we have studied motor imagery and mental fatigue extensively. We have studied motor imagery, mental fatigue extensively. The dark red colors that you see here in the topographic plot, they depict marked increase in delta, theta, and alpha. Okay, as I go from my first run to the last run, so I am having fatigue as I approach my last runs. This produces increased level of drowsiness and decreased level of arousal. So intelligent assistive devices that use motor imagery need to be adaptive for mental fatigue. And this is where we have come and proposed a new type of unsupervised method, which we call adaptive common spatial pattern, to really do the feature extraction. So for the uninitiated, a common spatial pattern is a statistical method that discriminates the spatial pattern for two classes. So experimental results show that higher separability of features extracted with adaptive spatial pattern is possible. How? Because after CSP, see, before CSP filtering, this is how the two-class excursion of the EEG should look like. So I have here a two-class excursion of EEG. After CSP, it should look like this, but fatigue spoils it. So what we have done, we have created an unsupervised adaptive method. Because fatigue is cyclical, so we could track fatigue, prolonged MI or motor imagery induces fatigue. So we continuously monitor it, and then we update the covariance matrix of each class by adding some regularization pattern. And once we do this, we use something called the Kullback-Leibler divergence between the training and the testing data to update our common spatial pattern. Now, the scale divergence is a measure of how the probability distribution of the target data diverges from the probability distribution of the testing data, and thus gives the similarity between the two distributions, and therefore is an estimate that is a very good estimate that checks the difference between the training and the testing and could very well update the common spatial pattern accordingly when it is fatigue and not fatigue. So based on that, if you see, a CSP was not able to really identify the signals, motor imagery signals, and adaptive spatial pattern could do this very clearly. Okay, so that clarity comes, and we use that in our assist as needed controller. So here is our two very typical prototypes available in the lab. One is a physical practice device, which is a soft hand exoskeleton, and other is a full-blown 5-finger hand exoskeleton for restoration of complete hand grasp functionalities, if that's possible. Okay, so we have fabricated this using again biodegradable materials. Okay, so now having done this, we focused on, and this is my last focus for the talk today, we have focused on how could one accelerate neuroplasticity. Remember, neuroplasticity is about creating new networks as you practice, is for rehabilitation. Either you physically practice or you mentally imagine and practice. So we have focused on three important things. Motor imagery, that's a standard traditional practice in rehabilitation. People are asked to imagine, and that's captured, and that's being passed to the device. We added this and we explored this and found that affordance, a concept that tells us what an object is to be used for, or predicts what it could be used for, or plus what you do with that object, observation of the action, they can also impact the same motor area as motor imagery. So we have looked at affordance driven activities that drives the same type of motor area, and we have said and hypothesized that if motor imagery is not looked at alone, but together with action observation, then maybe we'd have accelerate neuroplasticity. And this is what we have checked in our latest experiment. We have looked at pure action observation and asked people to record their EEG for pure action observation. The same group of people we have recorded for pure motor imagery and recorded them for combined AO plus MI. So we asked people to come and first look at a hammer being used. So that's action observation. We record their EEG. Then we'll ask them to imagine the same thing and record their EEG. And then we look at the combination and record their EEG. Now, when this is done, interestingly, we record what is called the event-related potential brain responses, that is direct result of a specific sensory, cognitive, or motor event. And what we have figured out is that the NI component and of the ERP for all three experimental conditions we observed. Now, for the uninitiated, the NI component is associated with visual discrimination and attention. And we could see that attention is highest when it is action observation plus motor imagery. Okay, so the NI component here is highest. It tells me that motor priming is strongest under this case. And we observe similar thing for N2. So N2 depicts the object affordance, what that object can be used for. Like I was showing a hammer. So people have imagined that you could do hammering. That's the primary object. Somebody could also imagine that you could smash glasses. That's fine. But the primary object is hammering. So that motor area of hammering in action activity, that gets tremendously primed. So our results shows very strong priming in combined AO plus MI. And what does that mean? That means that if you are trying to really rehabilitate a person and trying to use his assistive device and only relying on telling him to imagine and do stuff may not be good enough. It may be good to look at the thing and also play a video together with this. So our results showing stronger motor priming in combined AO plus MI condition and rather than pure AO plus MI has been very exciting for us, particularly near the premotor cortex, along with the supplementary motor area. We have seen this happening and it's very exciting. So we wanted to delve into it further and we then created what is called the low resolution electromagnetic tomography, the Loretta reconstruction. And so source density or source current density as an EEG parameter is estimated by such a reconstruction. And our results clearly again demonstrate that the affordance driven motor priming during action observation and motor imagery is strongest. So it indicates stronger electrophysiological and behavioral changes in this area, in this condition, combined AO plus MI. So what it means in plain terms is that visual guiding in AO plus MI leads to clearer mental simulation than MI alone, and therefore multimodal control paradigms holds promise, vision being one of the most significant modalities. So this is the premise that we have arrived at, and we want to look at that further. So looking ahead, now I'm just concluding in the next two slides. Looking ahead, we have done biomimesis of the human hand. We have done biomimesis of the human grasp. We want to do the biomimesis of the human touch. So if you know, there are mechanoreceptors in the skin that sense external stimuli, and an action potential goes to your peripheral nervous system, the sensory signal takes it to the CNS. In my recent experiments, I am trying to encode this in some non-invasive external stimulator, activating the mechanoreceptors at the residual limb so that the PNS is activated and the PNS then takes it to the sensory signal instead of a direct stimulation of the CNS. So indirect invasive stimulation of the PNS, I do a non-invasive external stimulation and signals go there. So what does that mean? That means that the grasp now would be embodied. That means the prosthetic hand the person is using, earlier it was only about the phantom limb control using some decoding of the EMGs. But now those will again, the complete loop will be closed. I'll be able to tell what it is holding or what is the feeling like through some transcutaneous nerve stimulation. And that would close that loop. So that would close the prosthetic loop for me for running for around 20 years now. The other thing that I'm going to look at and started to look at recently is this idea that the assist as needed should exploit the advancement in deep learning that's happening. So we are looking at some form of recovery process evaluation. And that recovery process evaluation is critical for determining how much effective the treatment has been, and particularly for delivery of assist as needed. So we are proposing an automated recovery process evaluation, which will collect kinematic features and task performance matrices, and then an analysis model would generate some form of indicators in line with those used in clinical practice for some recovery process indication. That is the idea. And then finally, the idea is to, based on that, build a reinforcement learning driven intelligent hand exoskeleton system or a rehabilitation system where I will learn an optimal policy for each individual via the recovery process indicators and the recovery protocols being delivered to him. So that would be the final thing. And that would be something that will really bring in automated recovery evaluation as well as automated assistance as needed for robotic rehabilitation, which would be really functional in its truest sense. So with that, I end my presentation and I would be more than pleased to take questions now. Thank you very much.
Thank you, Professor Hazarika. This is Udayan here. So now we can take up questions from our audience. Yep.
Yes, sir, please raise your hand so that will call out your name and then please ask your question.
There may
So
not be
then
any
do we see any
questions.
questions? I think anyway, Professor Hazarika has also given his details. So if anybody wants to get in touch with him regarding any questions that may pop into your head later regarding the presentation or regarding this topic, one can always reach out to him and ask him. So no questions? Okay, then actually, Hrithik, can we thank Professor... Oh, then Professor Saha is there. Hello, Professor Saha.
Maybe I'll ask. Hi, how are you? Maybe I'll ask a question. Shyamanta, nice to hear your so detailed work. And so this the hand which you are showing it. So is it for exercise purposes, rehabilitation? You said, right?
The first hand that I showed, we had created, and it is for a prosthetic hand, and some versions of it are for rehabilitation and for grasp studies of clinical studies of grasping. So we have hand versions which are prosthetic and plus for rehabilitation for clinical studies as well. But the other one is a pure exoskeleton.
Okay, so that would be quite interest to our IHFC, because yesterday we met some doctors from Indian Spine and Injury Prevention Center. So they have been working on various exoskeletons, for various exercise and therapy purposes. So I think this should be quite interesting to see that how it can be utilized for them. So I would be more interested to see more about that physiotherapy exercise purposes. Okay.
Great, sir. Thank you very much. I would get in touch.
Yeah. So
Yeah,
Pia, there is
it's
a
all
hand
about
raised.
Okay, so now Professor Saha,
CMA.
as I don't see any more questions,
No, CMA
No,
raised
there is a
hand.
question.
CMA raised hand.
Yeah. Please go ahead from CMERI, whoever is there, please.
please go ahead.
CMA is in mute. CMA, you're in mute.
Please unmute yourself. Yeah.
Yeah, again, good evening, Professor Hajarika. So it was really a fantastic, this presentation. I was really liked it very much, actually. So I just wanted to know one thing. You mentioned about this GASP synergy. Now this is this grasp synergies you are applying only for the grasp forces or also on the this hand movement, finger movements? You are targeting of holding different shapes and sizes of objects. So can you please give little more light on that? And of course,
so,
like how you are distinguishing between these two things? Like one is your movement, another is your force.
Yes, that's a brilliant question. So we have two types of synergies. When we talk of grasp synergies, we have two types of synergies. One is called the force synergy, which are the fingertip forces, and the other is called the postural synergies, which is the synergy of the angles. So if you have noticed, we are studying both. The synergy of the angles comes from the kinematics of the exoskeleton device or the data globe that we have created, and the synergy of the grasp force is from the fingertip forces. So our data globe for which we are recording, we have made it so very specific that the finger TPS gives us the fingertip forces that comes to us as separate data, and flex sensors over the whole globe gives us the postural data. So we look at the postural synergies and the force synergies is separately. Now coming back to how do you reconnect it to the EMG, that's a difficult question to answer. Reconnecting it to the EMG, distinguishing forces from posturals is something that we have not been able to very clearly identify tricks as of now. We are still working on it. And I should have a better answer how to look at the EMG and say this is the postural, this is the force. That's not possible at this moment of time, at least at my lab. But recording wise, we have very clear postural and force synergies coming to us. So recreating is easy, but only getting it from EMG is almost difficult.
Decomposition, yes.
Yes.
Because one lies in the null space, another is in the maybe range space, like how you are decomposing. Yeah, so
exactly.
It's difficult. Yeah. Okay, thank you so much. Yeah.
I can get back to you on this. This is a very interesting mathematical problem, actually.
Exactly. Yes. Yeah. Thank you so much. Yeah.
Thank you very much.
I think, Pia, we can go ahead with the felicitation ceremony. Yeah.
Okay, we can go ahead with the closure then.
Yes.
Okay. So, Professor Saha, I would request you to please offer a token of appreciation to Professor Hazarika for coming today and giving us this wonderful, enlightening talk. And Ritik, could we please show the brochure? The voucher.
So, Hazarika, so thank you. for your presentation, and this is a token of appreciation, a gift voucher of €150 sponsored by Springer.
Wow,
You
that's
can
brilliant.
order books with that,
Thank
and
you.
we'll communicate to you how to order the books. So please accept it.
Okay. Right now
Yes,
the
sir. Thank
voucher
you.
Thank
says.
you.
Okay, thank you very much. Thank you, sir, for being here. Thank you.
Yeah.
Loved it.
So voucher says €150, no name, but we'll send you a letter which will say
Don't worry.
how it is to be encashed.
Don't worry. Yeah, that's
Yes,
fine.
we'll send the
Yes,
details
sir.
to
We'll
email.
send you a letter. Yes,
Don't
Udayan will be
no
sending you a
problems
mail.
at all. Don't worry about that. It's fine. It's pleasure being here.
Yeah.
Yeah. Okay.
Thank you.
Thank you so
Thank you
much.
very much.
Thank you so much, sir.
Thank you all
And
Bye
have
of
a
bye.
you.
wonderful evening, rest of you.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.
Thank you.